Hi, I'm Kelly Marchisio, and I'm a PhD student at Johns Hopkins University, where I work on machine translation. And today I'm going to be presenting our recently published work entitled Controlling the Reading Level of Machine Translation Output. Oh, that's not my next slide. Oh, okay, this is the wrong version of my slides, so I'm just gonna go from memory. So this is probably about my 7th slide. But anyway, imagine that you have the situation where you're trying to explain to someone what is machine translation. And if you're explaining this to a child, you might say something like, machine translation is when you change one language into another language. And if you're speaking to an adult or pitching for some potential investors and you want to sound more professional, you might say something like, machine translation is the automated process by which we turn language from a source language into a target language. So as you can see, I've conveyed the same information, but I've used different words that are more appropriate to each audience. So as we can see here, users differ, so their translations should differ also. And we must keep in mind that there are other things other than what your sentence means that are important for how good your translation actually is. And one of those often overly neglected factors is who your audience is and what language is appropriate for them. So in this paper, we introduced the task of reading level control to machine translation. We developed 2 methods for controlling the reading level of output translations in neural machine translation, and we developed control over output readability score on 3 Spanish to English test sets. As I mentioned, lower complexity might be good for young children or language learners, but a really good case might actually be, say your native language is a language that's currently underserved by MT, a low resource language, and translations into your native language are currently poor. But say that you also speak a little bit of basic English. You may actually prefer to see a translation into basic English that you know is going to be reliable and semantically correct, rather than a poor translation that you can't trust in your native tongue. On the flip side of that, for higher complexity translations, this can be good for business and professional contexts, academic writing, and domain experts. So how do we score readability? We use 3 common English readability scores. The first is called Dale-Chall. This takes a percentage of the difficult words in your sentence over the percentage of the total number of words, and also has some account for the average number of words per sentence. We also have the Flesch Reading Ease and the Flesch Kincaid grade level. You can see these have something to do with the total number of words that you have versus the number of sentences that you have. Also, it takes account of the syllables in the words. Flesch Kincaid grade level roughly corresponds to the US schooling system. Again, if you want to hear more about these, I had notes on these slides I was going to read, so come to my poster and I have more details about them. So one thing that we noticed is that training data maybe unexpectedly, or you might expect this, does affect the translation reading level. I don't have much time to go into this, but basically, if you train a model on low complexity data, you're likely going to get low complexity data that comes out on the translation. And that's not something that your users can control. On the flip side of that, if you're training on higher complexity data, such as EuroParl, which is the European parliamentary proceedings, which use quite complex formal language, and then you translate a test set using that model, your data is going to come out likely in a more complex manner than it would in a simply trained system. And again, users don't have control over that. So one of the motivations for our project was to give users some control over that type of effect. So our data, we use approximately 2 million lines from the EuroParl corpus. We use 2 million randomly selected lines from Open Subtitles 2018, which is movie subtitles, typically lower complexity, more informal language. We also use approximately 15 million randomly selected lines from Paracrawl, which was scraped from the web. So for our data selection, we first score the target side sentence readability in the corpus. We then select sentences to include in our training data based on the percentile rank for readability. So you'll see we have a 30-30 setting, we call it. This means that we have scored the entire corpus for readability. We've assigned the bottom 30% to be our low complexity set, and we've assigned the top 30% to be our high complexity set. And then depending on the setting, we might use the data in the middle. So for our approaches, this is our baseline model. It is the default RNN-based encoder-decoder model with attention from OpenNMT. So the encoder and the decoder are 2-layer LSTMs, 500-dimensional hidden layer size, 500-dimensional word embeddings. Our first approach is inspired by Senrick et al. 2016, where we append a short text token to the end of each source-side training sentence, which corresponds to the matching target-side sentence's readability. So you see this sentence in Spanish. We have this odd token at the end, SZXC. This means that we have assigned this to the simple set. And in our complex set, we have a little different token that we append to the end of the source side of the training corpus. Our second approach alters the traditional encoder-decoder architecture by specifying a single encoder and 2 decoders. So when we're doing training, we're actually going to pair the encoder and the decoder that we want based on the complexity of the sentence that's going in. So when we have our simple tagged sentences, we're going to pair the encoder with the simple decoder and calculate the gradient based on that. With complex sentences, we're going to do the opposite pair. And then at test time, we are going to select the decoder that we want to decode with. So you see here that the encoder is learning a joint representation for what simple and complex language looks like, but the decoders are specifying themselves to be able to decode into a more simple or a more complex type language. So for our results, we have learned that good models do effectively control the reading level with little degradation in quality. On the left, we have our performance on News Test 2013 of the data tagging approach trained on Paracrawl. News Test 2013 is a very common test set in the machine translation literature. On the right, we have the equivalent translations using the double decoder models. And what you can see here is, in the first column, this 50-50 setting is, again, we have the bottom 50% of the data tagged as low complexity, the top 50% of the data tagged as high complexity, and you can see where the readability scores end up there. So DC stands for Dale Chall. Then if you look down that column, you can see that as we get more aggressive in what we're calling low or high complexity, that gap is widening. It's actually better visualized in this chart. In the blue, we have the data tagging approach. So you can see that with the data tagging approach, it's not quite widening that gap as much, but the double decoder approach is widening that gap quite high. The caveat here, which please come to my poster and discuss if you would like, is that the double decoder approach has some more loss in blue. And some of that's going to be good because we are intentionally swapping words out for either easier or more complex words. If you know something about how blue is calculated, swapping words in and out is going to affect that score. But it's not as bad as it looks, and we did some human evaluation on this, and we can explain how that went. Now for our qualitative examples, the first 2 come from the data tagging approach. The second 2 come from the double decoder approach. I'll read a couple of them out. So for the second one, the data tagging in simple mode decided to translate this sentence into, "This attitude is a terrible view of the future." And in complex mode, we have, "This attitude implies a deplorable vision of the future." In my opinion, implies is a more complex word than the word is, and deplorable is arguably more complex than the word terrible. So in my opinion, this is a success. Again, these sentences mean basically exactly the same thing, but we've chosen language that's more appropriate for our audience. And you can imagine how if someone is particularly learning English, they might not know the word implies or deplorable yet, but they might know is and terrible because those are arguably simpler. And in the third case, we have, "But my provocations are meant to start a conversation" in simple mode. And we have, "But my provocations are directed to initiate a conversation" in complex mode. Again, in my opinion, directed is more complicated than meant, and initiated is a more complex word than start. You'll notice, though, what I don't like about this example is that the word provocation appeared on both sides. I don't think provocation is a very simple word. So this isn't perfect, but it did change some of the words that we'd like. In an ideal setting, I believe that it should have changed the word provocations in simple mode also. Oh, well, I had some conclusions. They're not here, but in conclusion, we are the first people that have tried to control the complexity in terms of reading level of machine translation, both lowering and raising that reading level. Please come to our poster for more information about this and any caveats that we might have that I can't remember because they were on my final slide. Thank you.